So I'm going to be working at summation of a series. By the method of induction. Okay. And a subcategory is going to be called proof by induction. Shit. Now, I may be a wee bit out of practice, you know. What's the saying? You can't teach an old dog new tricks. But this wasn't in my A-level course 25 years ago, because I wasn't doing A-level 25 years ago. I was doing A-level 20 years ago. In fact, this wasn't even in my degree course. Okay, so the method of induction sums a series of, say, n terms, when the sum is given in terms of n. If you assume that the summation is true for one particular value, say k, then you assume that the sum of the first k terms is the sum of k. This is true for n equals k. Do you follow? Of course you do. Wee buns. So, let's see. Will I write that out? Okay. Method. Oh, remember I always mention in my videos how clumsy I am. Yeah, anyway. Let my left hand against the table. The method of induction sums a series. Maybe if you write this out often enough, it might make sense. Sums a series of, say, n terms. When the sum is given in terms of n. And the sum's usually going to be in the form of, you know, sigma r equals 1 to n of, you know, some formula in n. Okay? So, if you assume that this summation formula is true, if you assume true for one particular value or integer, particular integer k, where k is less than n, then you assume the sum of the first k terms is the sum of k. So this is only true for n equals k. So you assume whatever formula they give you is true for k. You then use this assumption to prove sum of the series to k plus 1. Is the sum k plus 1, i.e. by adding one extra term, the next term in the series. So by adding the next term in the series, the sum will have exactly the same form. But where before you had k, now n equals k plus 1. And then you prove, and you also must prove, you can either do it at the beginning or the end. Maybe at the beginning would be easier. Also prove that the formula is true for n equals 1. Because if the formula is true for n equals 1, and it's true for k, and k plus 1, well then you put in k being 1, and then you prove it's also true for 2. And if it's true for 2, it'll be true for 3, if it's true for 3, it's true for 4, and so on. So, this is the method for the questions. So, part 1. As I said, I did it at the end here, but let me do it at the start. Prove it's true for 1. And the second one, assume true for some n equals k. 3. Prove true for n equals k plus 1. So that's the method. Now, my problem is I looked at the AQA textbook online, and I looked at AQA past papers online, and their marking scheme, and the edXL past papers online and their marking scheme. And the method they use in the exams is different than the method they use in the textbook, which is weird. So, let's go on to some examples. This page is going to be an awful lot tidier than my initial working set. So, let's see, number 1. Show that sorry, there's no F. I've already made a mistake. Show that the sum of r equals 1 to n, 1 over r upon r plus 1 equals n let's check for 1. So you're going to have 1 over 1 upon 1 plus 1, which is equal to 1 times 2. That's a half. That's the left hand side. And then the right hand side, you have 1 over 1 plus 1, which is a half. So you've proved it's true for n equals 1. So now we're going to assume true for n equals k. So what you're going to have is sum of r equals 1 to k, 1 over r upon r plus 1 equals k over k plus 1. Okay. So on this side here, let's try it out with 1. So that r equals 1, you're going to have 1 over 1 times 2, this is 2. So you're going to have a half plus, and there's 2, you're going to have 2 times 3, which is 6, 1 over 6, plus, there's 3, you're going to have 1 over 12, plus dot dot dot. You're going to have up till k minus 1, sorry, up to k, you're going to have 1 over k and k plus 1. But now we want to bring this up as far as k plus 1. Well, this is then going to be plus 1 over k plus 1 on the outside of the bracket, and k plus 1 plus 1. Okay. So we've added this term here on this side of the bracket. So we had this being equal to k upon k over k plus 1. So now you have to add this to that. So that's 1 over k plus 1. And of course k plus 1 plus 1 is k plus 2. Missed out a wee bit of notation there. This is the sum of r equals 1, k plus 1. Okay. So, this here is the left hand side. Now let's tidy up the right hand side. So we have k over k plus 1 plus 1 over k plus 1 upon k plus 2. Okay, so let's give this common denominator of k plus 1, k plus 2. So that's going to be k upon k plus 2, because this will cancel with that to give that plus 1. Okay. So you have k squared plus 2k plus 1 all over k plus 1 upon k plus 2. And we can factorize that top line same as k plus 1 or k plus 1 plus 1. So we can see from above that is the same, where now we've changed n to k plus 1. So n is k plus 1, k plus 1, k plus 1 plus 1, k plus 1 plus 1. So it shows that the form is the sum of the same form with n equals k plus 1. So if it's true for k, then true for n equals k plus 1. Okay. Part of the way through that, I was thinking, this isn't going to work. Okay, so let's move on to another example. Okay, so it is prove by method of induction one times 2 plus 2 times 3 plus 3 times 4 plus dot 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 plus n upon n plus 1 is equal to a third n upon n plus 1 upon n plus 2. Okay, so part 1, I'm going to check for n equals 1. So if n equals 1, the left side is just going to be 1 times 2, which is 2. And the right hand side, we're going to have a third times 1 upon 2 times 3. So 2 3s are 6, and a third of that is 2. So yes, it's true for n equals 1. So now we're going to assume true for some n equals k. So that's 1 times 2 plus 2 times 3 plus dot 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 plus k upon k plus 1 is a third k, k plus 1, k plus 2. Okay, so now change to n equals k plus 1. So you want to move on to the next term here. So that's going to be 1 times 2 plus 2 times 3 plus dot 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 up to k upon k plus 1. But now we're adding on the next term, so you're changing k to k plus 1. So that'll be k plus 1 upon k plus 1 plus 1, which is k plus 2. Okay. And so previously all this here that was equal to that. Okay, so we have third k, k plus 1, k plus 2. So you have to add this on to make them the same. Plus k plus 1, k plus 2. Okay, so let's bring it down here. So, let's see. K plus 1, k plus 2, plus k plus 1, k plus 2. So, you can factor out, let's see, you could factor out k plus 1, k plus 2, and that's going to give you a third of k plus 1. Okay, and k over 3 plus 1 is the same as k over 3 plus 3 over 3, so it'll be k plus 3 over 3. Okay, so we've got k plus 1 upon k plus 2 upon k plus 3 over 3, which is a third, say k plus 1, just tidy this up a wee bit, k plus 2, k plus 3. So now this is now the same form as up here. This is the same form as above, where n equals k plus 1, because instead of k, you have k plus 1, instead of k plus 1, you have k plus 1 plus 1, which is k plus 2, and k plus 1 plus 2, which is k plus 3. So let's prove that. Okay. Okay, let's move on to another example. I'm skipping ahead in my notes because I didn't write down clearly what the next question was, and I don't want to stop. Okay, so the next one. Show the sum of r equals 1 to n of r upon r plus 2 equals 1 over 6 n upon n plus 1 upon 2n plus 7. Okay, so let's first of all check for n equals 1. So on the left hand side we have 1 times 1 plus 2, that's 3, which is 3. And the right hand side we have 1 over 6 times 1, then 1 plus 1 is 2, 2 plus 3, 2 plus 3, 2 plus 7 is 9, so it's 2 9s are 18, and a 6 of that is 3, so true for n equals 1. Now assume true for n equals k. So what we're saying is the sum of r equals 1 to k r upon r plus 2 equals 1/6 k upon k plus 1 upon 2k plus 7. Alright? Okay, so we're going to have, say the first term is going to be 1 times 3. So it's going to be 3 plus, then we're going to have 2. So that's 2 times 2 plus 2 is 2 4s, which is 8. Plus 3 will be 3 5s is 15. Plus dot 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 up to k. We'll say it's k upon k plus 2. So now we're going to make this, I'm just writing this out first like that. It's just my process. Let's make this r plus 1, r equals 1 to k plus 1. F r upon r plus 2. So that's there going to go up as far as k plus 1. We'll have k plus 1 on the outside. Or sorry, not the outside. Changing the outside to k plus 1. And then this bracket is going to be k plus 1 plus 2. So that's k plus 3. So as I said, all this here before, that's equal to up here. So that's going to be equal to 1/6 k, k plus 1, 2k plus 7, plus k plus 1 upon k plus 3. So again, this is, I don't know if I can put it over here, just bring it down here. So let's say that's equal to 6 k, k plus 1, 2k plus 7, plus k plus 1, k plus 3. So now we can factor out the k plus 1s. And that's going to give us 1/6 k, 2k plus 7, plus k plus 3. I won't bother with the brackets because there's enough. There's no change in operators. Actually, 1 second. What we can do instead of that is bring out the 6th. Bring out the 6th as a common factor as well. So 6 k plus 1. So then that's going to give us k upon 2k plus 7, plus, and then you multiply the second bracket by 6 because that will then cancel out, k plus 3. Okay, so it's equal to 6 k plus 1. We'll expand the brackets. You're going to have 2k squared plus 7k plus 6k plus 18. And that's equal to 6k plus 1, 2k squared plus 13k plus 18. Which is equal to 6k plus 1. Now let's factorize. I see up here they have the 2n at the end, so we'll put it that side. 2n and n. Say n is meant to be k. Distracting myself. Okay. 2, and that's going to be plus 9. So we have k times 2k is 2k squared, 4k plus 9k is 13k plus 18, so that's that. So now, if you look at this one from above, k becomes k plus 1, yep. K plus 1 is k plus 2, yep. 2 times k is going to be 2 times k plus 1, which is, let's show you, that's going to be 1 over 6. K plus 1, k plus 1 plus 1. Don't think that second bracket's necessary. We're not there anyway. 2 k plus 1 plus 7, which is the form we wanted, which is of the same form